The last example of hypothesis test for two populations is a matched or paired samples hypothesis test for the mean. And in the OpenStax Introductory Statistics textbook, this is section 10.4, matched or paired samples. And in the Lumen Introductory Statistics with Corequisite book, this is in module 10 for hypothesis testing with two samples under Introduction and hypothesis testing with paired samples. So here we have a situation where we have used simple random sampling to select a usually small sample, and we will be doing a dependent population comparison. So we will have a sample of the same individuals or pairs of individuals, and we will actually collect two measurements from them. And the two samples must be equal to each other because they are dependent on each other. So if it is a before and after situation, then we will have the same number of individuals that we are testing before and after. If they are paired because they have a relationship to each other, then we are comparing the pairs between them. The differences are calculated from the matched or paired samples, and these differences form the sample that is used for the hypothesis test. So actually a single variable is the difference that occurs between each pair. We don't have two separate populations that we calculate the means and then the difference of those means. Instead, we have a sample of pairs, and for every one of those pairs, the variable that we are trying to evaluate is the difference between the values of the variable of the investigation variable. Either the matched pairs come from a population that is normal, or the number of differences is sufficiently large, so the distribution of the sample mean of differences is approximately normal. In a hypothesis test for matched or paired samples, subjects are matched in pairs. These are dependent samples. They are not independent. The differences are calculated from the data used, and the test is a single sample of size n. So we only have one sample. That sample has a variable, again, of investigation being the differences between the values of the data. The population mean for the differences, mu sub d. So it's not the mean of a particular population, and a variable on investigation is the mean of differences, is then tested using a student's t-test for a single population mean with n-1 degrees of freedom, where n is the number of differences. Your test statistic or t-score will be, again, the sample mean from the differences minus the population mean from the differences divided by the standard error of this distribution, which is the standard deviation of the differences divided by the square root of n. An example here is a study that was conducted to investigate the effectiveness of hypnotism in reducing pain. Results for randomly selected subjects are shown in the table below. A lower score indicates less pain. The before value is matched to an after value, and the differences are calculated. The differences have a normal distribution. Are the sensory measurements on average lower after hypnotism? And we want to test that at the 5% significance level. So here again we have some people who get treated with hypnotism, and we check their pain levels, and we have the before pain levels, and then we have the after pain levels, and we want to test the claim if hypnotism is effective to reduce the pain levels. So to start this test, we have to find the differences first. And if we find the differences as before minus after, then we will have 6.6 minus 6.8, and this difference will be negative 0.2. This is an example of a subject or an observational unit who actually ended up having higher level of pain after hypnotism. For subject B, we have 6.5 minus 2.4, and that is 4.1 when I subtract them. And this person had a lower level of pain after hypnotism. For subject C, the difference is 1.6. For subject D, the difference is 1.8. For subject E, 11.3 minus 8.1, the difference is 3.2. For subject F, it is a 2.0. For subject G, 6.3 minus 3.4 is a 2.9. And for subject H, 11.6 minus 2.0 is a 9.6. And what we want, or what the Art of Stat will give us when we use our technology, it will calculate the mean, the standard deviation, and the count for all of those. For the before data, for the after data, and for the variable of interest that is the differences. So I have created an Excel file where I did insert over here the data, the before and after, and then I subtracted row 18 minus row 19 to find the differences here. And then under the column for the mean, I asked Excel to find the average. So here I found the average of row 18, which is the before, and the average of row 19 and the average of row 20. The standard deviation, remember these are samples, so I used standard deviation.s for before, for after, and for the difference. And then I used the count function to make sure that I have the same counts, and I was expecting to have the same counts since these are dependent samples. So we want to keep track of these numbers. We actually do not care for the individual averages and standard deviations. We only care for this row, which I'm going to highlight here with a bright yellow. So let's fill out our notes with these values. So the observed difference is the 3.125, which is the sample mean of the differences. And the standard error will be the S that we found divided by the square root of n. So it will be the 2.91 divided by the square root of 8. And I'm going to try to do that in Excel. So here for the observed differences, I will just copy the mean of the differences that I found. And for the standard error, I will say that this is the standard deviation of the sample of the differences divided by the square root of the size of the sample. So I will have a standard error of 1.02935, which is 1.02936 if I expand that cell in Excel and I can see more digits of accuracy. The null hypothesis in the test for dependent samples is that the mean difference will equal to 0, which means there was no difference before and after hypnotism. And the alternative hypothesis is what I'm trying to check, is whether the sensory measurements on average are lower after hypnotism, which means that the difference between before minus after will be a positive difference. So our alternative hypothesis will be whether the mean of the differences will be a positive quantity to indicate a higher before pain and a lower after hypnotism pain. Alpha is 0.05. And the test statistic T will be the observed difference, the sample mean, 3.125, minus the mean of the population per our hypothesis test, that would be a 0, divided by the standard error, which we found it to be approximately this 1.029346. It's better to have exact values. And in Excel again, that will equal to the observed difference minus 0 divided by the standard error that I found, and this value is a 3.03591. And then I need to find the p-value. Remember, this is a t-distribution, and it will be the probability of finding a mean difference of 3.125 or greater, since this is a right tail test. So again, I'm going to do that in Excel for now. I will show you how to do it in Art of Stat. This is my test statistic, and my p-value will be so if I use the t-distribution, I can do a right tail, returns the right tail students t-distribution, which is what I want. If I was doing just the t-distribution, I would have to subtract from 1, which is 100%, because the t-distribution will give me the left tail. But there is an option for a right tail, so let me select that. And it says, what is your x? Here is my x. This is the test statistic, comma. And then it says, what is your degrees of freedom? And my degrees of freedom will be the n, which is this number 8 up here, minus 1. And it tells me that the probability is 0.00948. That's the p-value. So this sample of 8 differences actually is a very unusual sample if it comes from a distribution that assumes that the mean of the differences between pain levels before and after hypnotism will be 0. So my actual data is a very unusual outcome per the hypothesis, the null hypothesis. Therefore, I have enough evidence to reject the null hypothesis. And my conclusion will be that at the 5% significance level, the sample data provides sufficient evidence to conclude that pain levels are indeed lower after hypnotism. Remember that in our decision, we only reject the null or fail to reject the null, and in our conclusion, we only claim that we can support the alternative or we cannot support the alternative hypothesis. Do not mention the alternative in your decision, and do not mention the null in your conclusion. Now, in terms of Art of Stat, when you are in the web apps and you compare two means, you can select in Art of Stat 2 dependent samples. At the top, this is a tab of 2 dependent samples, and you can enter your own data, and the response variable will be a pain level, and the group 1 will be the before, and the group 2 will be the after, and the group 1 data, let's see if we can just copy from our book online or from our notes. Hopefully, yes, it worked. And then group 2 data from our group, book online or from our notes. And I'm doing a significance test. I want it to be greater than. And I want to show the degrees of freedom. They are 7 as expected. Notice here that it does provide you the mean, standard deviation, and n for the before, after, and the differences group, but you only care for these differences. That's your sample, and your variable is the differences on pain levels. You see that we have an observed difference of 3.13, which agrees with ours that was 3.125. We have a standard error of 1.03, which again agrees with our 1.029346. We have a test statistics of 3.036, which agrees to ours, that was 3.0359. The degrees of freedom are 7, and the p-value here is 0.0095, which agrees with our p-value of 0.009478. So you can see if by clicking the test decision, you actually will see the test decision. So here, sometimes ArtofStat does not provide you the answer, so it is very helpful if you know how to use a very low p-value. You will have in tests and exams, you may have to sketch this t-distribution and label the axis. The variable here on this axis are the t-scores for the mean difference between pain levels. That's what that variable will be. Remember that your variable is the mean of the differences, and then this will be the t-scores for those. And based on this p-value, you can then decide to reject the null hypothesis and conclude that at the 5% significance level, the sample data can support the alternative hypothesis. Now, without going into all of this manual work, let's try to actually answer this using ArtofStat. The next example that says 5 ball players think they can throw the same distance with their dominant hand, the throwing hand, and their off hand, the catching hand. The data were collected and recorded in the table below. Conduct a hypothesis test to determine whether the mean difference in distances between the dominant and the offhand is significant. Test at the 5% level. Here, our null hypothesis will be that the mean difference will equal to 0. There is no difference between the dominant hand and the offhand. And the alternative hypothesis will be that the mean difference is not equal to 0, since it doesn't ask us to decide either way if the dominant hand is stronger than the offhand. And again, without having to do all of this work ourselves, we will just enter the data in ArtofStat. So here I'm going to have the throwing distance. And this will be the dominant hand. And this will be the offhand. And I'm going to delete the data here and enter the new data. So for the dominant hand, I'm going to enter those. And for the offhand, I'm going to enter those. And I need a significance test at the 5% level. I want it to be a two-sided test. The level of significance is 5%. I want to show the degrees of freedom. And here I have 5 differences. The mean was 21.8, which is our test statistic. And that the standard error was 13.59 divided by the square root of 5, which is 6.08. The test statistic for that was a 3.587. Because it is a two-sided test, we have a negative 3.587 and a positive 3.587. They create a p-value in both tails of a total of 0.0230. So here I get a p-value of 0.0230, which is less than alpha. Because of this, I will reject the null hypothesis, and I have enough evidence to support the alternative hypothesis that there is a difference between the dominant and the offhand, which is significant. So again, you can use the results from the screening art of stat to fill in all the required areas if you are taking a test, or if you are required to report the test statistic. If you need more accuracy than what art of stat is giving you, you need to be able to do that in Excel, and Excel will give you higher accuracy. If you are asked to put a label here on the axis for this t-distribution, you want to say that these variables shown in this axis are the t-scores of the sample means of the differences in distance of throwing for baseball players between the dominant hand and the offhand.